Okay, so here we have an example of a classic projectile motion problem. This can be a lot of different things, but the keys of this particular situation is that we've got an object that is a projectile from where it is launched over here at the origin to where it returns to the same vertical level over here at the end of its trajectory. All right. That is key, because if we don't have that, well, then this problem, well, one, is asking a different thing, but also the mathematics become a little more complicated to answer the question, what is the range of this projectile? I'm using a more concrete example of an arrow shot from a bow, but you could think about a lot of different projectiles that might have something like this happening. All right, we're given some actual numbers to deal with rather than just symbols, right? We're told that the initial velocity of this projectile is 60 meters per second in magnitude and directed at 40 degrees above the horizontal. And this diagram reminds us that when we have this case of following sort of the whole parabola, starting and ending at the same vertical level, then we start out with some relatively large amount of initial vertical velocity that gets smaller and smaller and smaller until it gets to momentarily zero up here at the top, and then gets bigger and bigger and bigger and bigger until we reach the end, when it's just the instant prior to it hitting the ground and experiencing an acceleration different from gravity. Okay. With that set up, let's jump right into it. We want to find delta x, and usually a good policy with these kinds of problems is to just try to go straight at the solution if you can. And if you look at those equations of motion that we have for projectile motion, our sort of simplest model of two-dimensional motion, well, we've got an equation for delta x, right? There's one that looks just perfect for our purposes until we look farther into it, right? So this would tell us what we want, and we can figure out the x component of the initial velocity, right? We have the velocity vector, and we can find, using a little bit of trigonometry, the adjacent side to that angle, which is the initial horizontal component of the velocity. Okay, so this can be found. We haven't found it yet, but it's easy to do. However, we run into a problem when we get to time of flight. We do not know how long it takes, or rather, how long the projectile spends in the air when it's doing this path that we see in the diagram. So we have to go get it. And if you look at the equations of motion in the horizontal direction, really this is the only one, in a sense. The rest of it just tells us, okay, well then the initial horizontal component of the velocity is the same as the final component of the horizontal velocity, or horizontal component of the velocity. It's a bit of a mouthful. But this is the only one that involves time. This is the only one that involves delta x. So because time, though, marches on whether we're moving vertically or horizontally, we can appeal to our vertical equations of motion to find out what that time is. And if we look down the list of the bunch that we've got there, and we look at solving for time, well, we've got a couple of different options. We've got this one, which is a distinct possibility. We could use that. Oh, my toddler is upset about something. Oh my. Or we could use this one. Oh no. Poor baby. Or we could use this one, right? Both of those involve time. And in terms of the information that we can easily access without sort of making an extra logical leap, I'm going to argue that probably this one is the simplest route. Though if you make certain assumptions, which are good ones about this, for example, that the downward final velocity here is the same magnitude as the initial velocity. Turns out that's going to be the case over level ground, where we're leaving and returning to the same vertical point or same vertical position, just a different horizontal one. But anyway, we'll proceed along these lines. You can go the other way and get to the same result. Now, if we look at this equation, we start saying, okay, well, we've got time. That's what we want to find, and then stick back over here to find delta x. We know what the acceleration in the vertical direction is. We'll come back to that just in case you don't know what it is off the top of your head. We can calculate this, and we know what delta y is. Okay, so I've made a couple of claims. I've made a claim that we know what this is, and I made a claim that we know what this is. And if you're not familiar with projectile motion problems, then maybe you're not seeing how it is that we would know those things. So, for starters, this comes from the definition of projectile motion. There's only one acceleration for a projectile, and that's downward and equal to g, right? It's only under the influence of gravity. It's part of the definition of being a projectile. So a sub y is going to be negative g, or negative 9.8 meters per second squared. And delta y, for this situation specifically, where we're starting here and we're returning to the same vertical position, right? Y is 0 at the beginning, y is 0 at the end, so delta y is 0. Okay, there's no change over the whole trajectory in the vertical position, right? Yes, it goes up, and yes, it comes down, but it starts and ends at the same point, so delta y, that displacement, is 0. So that considerably simplifies the calculation, solving for time in this equation. All right, so let me bring it up over here. This side turns into 0, and we can write out v0 sine theta. Theta is just going to be that 40 degrees times time. And let me get rid of, actually, get my eraser here. Minus 1/2 gt squared. When you get to the edge of the screen, it always goes sort of fatter like that in the handwriting. Oh well. And then we can divide out a factor of t, because the left-hand side is 0. That does mean that t equals 0 is a solution to this equation, but it's kind of a trivial one. It's like we haven't started throwing the projectile yet. We're not really interested in that solution. So we can safely ignore it, and we're left with 0 equals v sine theta minus 1/2 gt, right? We've canceled one factor of the t's. Now, we can solve for t here. We subtract this factor from both sides, and then we divide out by 1/2 g. And what that gives you is this expression, a 2 out front, and a g there, and a t there, okay? Now, we could have put in numbers here, but I'm going to try to demonstrate something, a more general equation for range. And that's why I'm not putting in the numbers. But you could totally get a number for time here, right? We know everything on the left-hand side of this equation, and so we could get a number, right? And you should feel free to do so. Now, we have an expression for t. We're going to take that expression, we're going to substitute it back into the equation that we have over here for delta x, the thing that we're trying to find. Okay? And we're left with something that looks honestly a little ugly, okay? But we know all of these numbers, right? This here is just the x component of the initial velocity written out in terms of the magnitude of that velocity and the angle. And we know that angle, that's theta. We know this, that's the magnitude of the initial velocity, so I'll just drop the arrow from that for the symbol. We know what g is, and so we can plug in our numbers and get a number. If you do that, you get a fairly sizable number. I think, here, let's type it in. I'm actually not that concerned with it. But you get 2... Okay, so you get about 360 meters if you actually plug in the numbers for this thing, okay? However, let me do one more step, and that will give us the classic sort of range equation over level ground, because if we use a trig identity to simplify this, and the trig identity is that 2 times cosine theta sine theta is equal to just sine 2 theta. Then if we simplify this a little bit, we get the following. Let me get a better thing there, better handle on that. Put this back. Something like that. So this is the range equation over level ground. Over level ground. Let me say that one more time. Over level ground. Please do not misapply this equation. I'll give it to you, right? If you happen to run into a situation where your projectile is leaving from and returning to the same vertical position, well, then this equation will give you the range, or various other things if you already have the range and are looking for initial velocity or something like this. But never apply it to a situation where, say, you're, I don't know, throwing a grappling hook up onto the top of a wall, or who knows what situation, okay? Taking a shot in a basketball game where the end point is at the basket and the release point is below the basket. That's not level ground, and you're not returning to the same vertical position you left from, and here, we'll give it some exclamation points. You will get nonsense for your answers, okay? So that's a nice equation to have in your back pocket. It works really well and is really simple compared to, all the rest of the things we did just here for problems like this. But be careful of when it applies. That's all I'll say. Okay, so 360 meters for our example here, and just a little bit of a flavor of how you work through a projectile motion problem. We'll do one more, and I'll probably go and record that right now. Thanks for listening.